So the first part of this class has a lot to do with functions. Actually, the whole class kind of does. We've talked about polynomial functions. We're going to talk some more about them. I think we mentioned rational functions. We're going to talk some more about them. Coming up, we're going to. It's not working. Can't see. We're going to look at exponential functions. If you haven't run into these before, don't worry. We're going to cover them. If you have, feel good that you have a little up on where we're going exponential. We're going to talk about log functions, and then the third half of the class is going to be dominated by trigonometric functions. But along with these specific types of functions, we're going to talk about, we've been talking about properties of functions. We've mentioned a few properties already. We mentioned something called even and odd. These are properties that well, not every function will have them, but any function could have one of these two properties, or none of the above. So, with that in mind, today we're going to talk about something called a one-to-one function. And this is going to feed in to, we're also going to talk about inverse functions. But it's good to understand what a one-to-one function is before we talk about inverses. I'm going to take only a 20-second break here to get some defog in my glasses. Another foggy day out here. That way I can follow all the rules. Okay. Oh, I guess I'm jumping the gun here. Was there anything in the homework anyone wanted to ask about before we go further? You always just interrupt me if I forget about this. All right, well, you can bring it up after the, if something comes up, you can bring it up after the break also. Okay, so let's look at a simple example of a one-to-one function. We're going to take the mapping, f of x is x plus 4, and we're going to have a very small domain here. It's going to be 1, 2, 3. So, of course, 1 goes to 5, 2 goes to 6, and 3 goes to 7. So, and this is the whole range here. So for each member of the domain, there's exactly one member of the range. And each member of the range only has one member of the domain that's mapping to it. That's pretty much the definition of a one-to-one function. Let's look at something for a second that's not a one-to-one function. Let's just take f of x mapped to x squared. And again, we're going to have a very simple domain here. So 1 will go to 1, 2 will go to 4, and negative 2 will go to 4. This is not a one-to-one function because it's a function, but we have two elements, 2 and -2 being mapped to 4. So it doesn't have this property. There's another way to state this, which is we could say f of x1 equals f of x2. That's the item over here in the range. And x1 equals x2. Okay, this is kind of a math idea. We have to think this through. If we have two elements over here, well, over here we'll say, and they both, well, we have 6 and 6, right, that we got here by some x. It has to be the same x brought us there. That's what this is stating. Have we mentioned the term contrapositive here? No. Okay. Well, you might or might not remember this from geometry when you were doing proofs, if you were doing proofs in geometry. But if you have some theorem, so your theorem might be P implies Q. This is some statement. You have P, then you have Q. The contrapositive is the statement not Q implies not P. Now this is really really important idea in mathematics, very fundamental. And it's good to kind of have some feel for why that might be true. In other words, if this is true, this is automatically true, and vice versa. So let's think of an example. Someone else thinks a good example. You're welcome to throw it up here. This is a stupid example. You have to give me a little leeway here. An animal goes moo. That's my P. The animal is a cow, right? So the contrapositive would be an animal doesn't go moo. It's not a cow. You know, think up a couple of these to convince yourself that these are kind of saying the same thing. It's nighttime. The sky is dark. The sky is not dark, it's not nighttime. Okay, so this is just something good to know. There are other things along these lines you should know. There is Q implies P. That's not the same as P implies Q, and it's not always true. That's the vocabulary just going out the window. It'll come back to me. P implies Q, and you have the converse. And if you have both a proposition and its converse true, we often will say P. We might write it like this, or we might use, instead of saying if P then Q, we might say P if and only if Q. And we'll write it that way. Okay, the reason I bring this up is that we can form the contrapositive here, which is x1 is not equal to x2. This is for a one-to-one function. Then f of x1 is not equal to f of x2. And again, you might want to think about why these are, let's see, put in if then. You might want to think about why these are the same statement. Now, where this can come in handy is sometimes you're trying to do a proof, and you want to prove this statement, but it's hard for than proving this statement. If you prove this statement, you're done. All right. One-to-one function. This is not working. Okay. Let's take a look at what might be a one-to-one function. F of x equals ax plus b, and the domain and the range here are all real numbers. Right this way. So let's see if we can prove this. So let's assume this is the case. That is ax1 plus b equals ax2 plus b. And we're just trying to show that x1 equals x2. Well, using our rules for manipulating equations, I can subtract b from both sides. I get ax equals x2. And I can divide both sides by a. And I get x1 equals x2. So that's just an example, very simple proof that this function is always one-to-one. Okay. Another well-known function you should be aware of, that's one-to-one, is f of x equals x cubed. At least have a passing notion of what this looks like. As x gets very large, f of x gets large even faster. As f of x becomes negative, x cubed becomes very negative much faster. This is a one-to-one function. Yes, one-to-one. This function, however, the way we normally define it, f of x equals x squared on all reals, it is not. And if we draw a picture, you can kind of see why right away. Because there are, let me get this right. There are values, x minus x, which map to the same point. Now, this might suggest something like something we've done before. We had, as a way of knowing if something's a function, we had the vertical line test. Here you can see that we can have a horizontal line test. This horizontal line test tells me if there's a horizontal line that passes through more than one point, it's not one-to-one. And no point is on, if if no line passes through 2 points on the graph, such as here, then it is a one-to-one function. So that's the horizontal line test. I guess I should write that down. So if you see a graph of a function, it makes it real easy to tell right away. Now, recall that a function is both a mapping and a domain. And here we've got the domain of all reals. It is possible, when you have something like this, which is not a one-to-one function, it is possible to make it into a one-to-one function. We do this by restricting the domain. Let's just say this is now a function with domain x is greater than or equal to 0. And now the graph of the function is just this limb of the parabola. And of course it passes the horizontal line test. Again, the term for what we're doing here is we restrict the domain, and we can make it into a one-to-one function. It's not the same function, it's a different function. F of x equals x squared on all reals is different from this function. But we can, when we need to, we can get a one-to-one function out of this. And we'll see a need to do that in a few minutes. All right. Fogger is not working. It must be really humid today. All right, any questions about this? This is one-to-one functions. I guess if you're following in the book, this is going to be section 2-8. Okay, so why all this concern over this type of function? So now we're going to look at a new type of function. It's really not a new type of function. It's just a function like any other function, what we would call an inverse function. So let's start with, we have some function f of x, and it's going to take numbers to some range. I guess we could call this x plus 4. So we're taking, this is f of x. Now what if we wanted to get from these values back to the original values? Well, you can see right here that the way we're going to do that is we're going to subtract 4. We call this function the inverse function, and we will typically write it this way. Now, I want to be very careful about this, because this can be this is a point where it can be very confusing. Later on in the class, we're going to take a function like sine of x, and then we're going to write it this way, sine 2 of x. And what we mean is sine of x squared. When we write f of x to the minus 1 here, we don't mean 1 over f of x. We don't mean f of x reciprocal over to the minus 1 power. This is not what we mean. It's not f of x to the minus 1. When you see a minus 1, you want to always think inverse. So in this case, our inverse is just x minus 4. All right. The inverse function, again, we have a function, and the inverse function just takes everything back. Now, maybe you can see why this one-to-one idea is really important. What if this was not a one-to-one function? Well, how do we get back from 6, 2, and 3? We don't really know where it came from. I mean, we could just say 6 goes to both 2 and 3, but then it's not a function. So these two go hand in hand, inverse functions and having the one-to-one relationship. All right. All right. So we're gonna try and find some inverses. Let's do a few examples. Get a field. So for something really simple, f of x equals 2x plus 6. So here's the method I suggest whenever you're asked, find the inverse function. Go through these steps. First thing you do, replace f of x with y. That's step 1. Second step, switch the x and y. Switch them. And then the third step, solve for y. Well, we know how to do that here. Subtract 6 from both sides. And then if we just divide by 2, we're going to get y equals x minus 6 over 2. Now this is an easy example. It's not always quite so easy. Sometimes we have to work a little harder. Let's try another fairly straightforward, simple example. F of x equals x squared. Okay, so y equals x squared. That's the first step. Switch the variables, x equals y squared. And now we want to solve for y. So how are we going to do that? Well, here it gets a little tricky. We could say y equals square root of x. Or we could say y equals minus square root of x. Can't say both. We want an inverse. We're going to have to go back here and look at the domain. The domain was all real numbers. But for each of these functions, we're going to have to restrict the domain. So if we want to make it square root of x, the domain has to be x greater than or equal to 0. We want that's fine too. But we can't have x less than 0 because we're finding the square root. Well, you know, I guess the last step is you want to replace y with this symbol, the inverse of x. It's 6 over 2. And here, let's say inverse square root of x. Okay. Now, I want to show you something. I didn't find this obvious at first. After a while, it kind of grew on me. Let's take our function here and our inverse, and let's graph them. Again, I'm restricting this domain here to x greater than or equal to 0. I guess I should make that clear. So square root of x kind of looks like x squared kind of looks like this. Square root of x kind of looks like this. Now, if I drew this really well, and I draw the line here, y equals x, you might notice that these two are reflections on each other. It's kind of a trick. If you ever see a function something like this, and if you're artistically inclined, you can get your brain to switch these things. Kind of have to look off like that. You can find the inverse by simply reflecting the function across here. Also, if there's a problem with the domain, it's going to show up right away. We'll no longer pass the vertical line test. You can see right away we have to limit it. This idea, it really makes a lot of sense if you think about the fact that if you've got a point x here, the point on the curve is x comma y. So the function takes x to y. But if we want a function that's going to take y, that's over here. See, I better draw this right. It's going to take y. Oh, that's way out here. Back to x. It's going to be a point that's kind of across this line here. This is going to be whatever value x and y were, it's going to be switched. So that's another way you can think of an inverse function. If you have a bunch of points, x, y, you just reverse the x and y. That tells you about the inverse. All right. Some questions about this? Hello. Hello. all right, I got it. All right. Final important feature of inverse functions. If I have a function f of x, and I take the value that x is mapped to, and I plug it into the inverse, what do I get? What do I get? Get x. Absolutely. So a feature of all inverses is, if you take the inverse of the function, you're going to get x back. Likewise, if I just take some x and plug it into the inverse, and take the result of that and plug it into f, what do I get? Get x. You might want to notice that this designation of function and inverse is kind of arbitrary. You could switch them, right? I could call this the inverse and this the function. It's the same thing. That's what I mean. There's nothing special about it being an inverse. It's just telling you what it is relative to a function. Why don't I at least give an example of this? Let's take the example we used before. We had f of x equals 2x plus 6, and inverse of x was what? X minus 6 over 2. So let's see what f inverse of f of x is. Well, again, here, we just covered this last week, but here we are composing these two functions. This is going to be f inverse of 2x plus 6. So how do I evaluate this? Well, I plug 2x plus 6 into here. 2x plus 6 minus 6 over 2. Well, you can see where this is going. The 6 is canceled, 2 is canceled, and I just end up with x. You might want to try it the other way. You might want to plug x minus 6 over 2 into 2x plus 6. See if you get the same thing. Time check here. Okay, I'm going to take a break here. Okay. So, our next section, we're going to focus on quadratic functions. A quadratic function is a function of this form, f of x equals ax squared plus bx plus c, something I'm sure you're all familiar with, where a is not 0. That would be a linear function. The graph of this is always a parabola. The parabola might move around and it might be upside down. Anyone recall how you can tell just by looking at the equation whether it's right side up, right side down, holds water, or trips water? Anyone recall? Yes?
Is it like a negative coefficient or a positive coefficient?
The leading coefficient. The leading coefficient is positive, it holds water. If it's negative, it's water's going to drain. You can kind of like sense that. If you realize that x squared is always going to dominate as you get far away from the center. So then, if this is positive, it's going to be going up as it goes away. That's one way to think of it. So yes. Because it's a parabola, it's going to have a vertex, which will be the minimum or the maximum of the function. This is one standard form, but we have another standard form, which is for a quadratic function. We can say y minus k equals a times x minus h squared, where hk is the vertex. So one feature of putting it in this form is you immediately know where the vertex is. The a, well, we already talked about how if it's positive, it's going up, if it's negative, it's going down. But it also tells you a bit about the shape. So, now I have to try and draw this with some accuracy. This is x squared. In particular, those are the points 1, 1, and negative 1, 1. What would you think would happen if I call this f of x? If I were to graph g of x equals 2x squared, what would that do to the shape? Yes, I saw that hand gesture. Yes. Think about this for a second. What happens as we move outward? Since there's a 2 in here, it's going to go up faster. Okay, it's going to go up like this. Whereas, once in a blue moon, I can use colored chalk to effect here. Instead, this number is smaller than 1. What happens then? Well, it takes longer for it to move up, so it flattens out. So it's shallower. And this is, the bigger the number, the steeper it is. Okay, so we have an idea what to expect. We're gonna try out this form of the equation, but what happens if I just give you something in this form? Let's take a look. An example, 2x squared minus 12x plus 13. So we want to graph that. Now, today you use your graphing calculator. desmos. You can plot points. So the point of this exercise isn't so much because we want some fabulous new way to graph it. We want to understand more how we get to this form here. So how do we do that? Well, first thing we want to do is remove this leading coefficient. We want to factor it out. We'll see why in a second. Next thing we want to do here is we want to complete the square. I think I talked about the fact that we're not going to be solving quadratics this way that often. The skill to complete the square is going to come up a lot. And here it's just come up. So what is it I need? Put this out here. What is it I need to put here, to add here, to complete the square? It's 9. Okay? So everyone see how we get that. If you don't see how we get it, recall you take the b, which in this case is 6, you divide it by 2, square it. Okay, so that's 9. But we can't just arbitrarily add 9. We have to subtract 9. Okay? Well, now we know this is a perfect square. If it's a plus b squared or a minus b squared. In this case, a minus b is x minus 3 squared. Plus, what do we got here? 18 plus 13, 28, 31 over 2. All right. I'm gonna do this a little differently. Go back. I think this will be make a little more sense. I'm going to call this y. That's my y-axis. I'm going to add 9, as before. But now I'm going to add 9 to this side. But since this is 2, what do I have to add over here? I'm adding 9 here, that's really 9 over 2. So I add 9 over 2. Oh. That's the problem. Coming out different on my notes. I made a mistake on my notes. Okay, so we have y plus 9 over 2. This is really 13 over 2, right? So I'm going to bring that over. And now I have my perfect square. Okay, so 9 minus 13 is minus 4, is minus 2. I think I got the right answer. I'm doing this right. This is the simple math. All right, somebody can find the error here later. But that's the idea. Now we have this in the form we want. We can see that the center, or the vertex, is going to be at 3, 2. So let's see how that works. So 1, 2, 3, 1, 2. And as before, there's a 2 in front, so it's going to be narrower than just the x squared parabola would be. thing we might have wanted to look at here, because it would help to graph it, is to see if this happens to have any zeros. So we can do that by either using the quadratic formula, or maybe in this case, we'll be better off just finding the determinant. That would be b squared, 144, minus 4 times 2 times 13. That's 8 times 13, 804. Yeah, I've gotten my out to lunch today. Not coming out right. I'm making terrible mistakes as people aren't raising their hands. What that means? That means we start over. Okay. Yes?
I think there's just some like subtraction error, because when I tried to solve it, I got negative.
Yeah, I know I was doing something wrong up
Or
there.
not for this one, it was for, wait. Yeah, it was for this one. What I did was, because it was 2 parentheses x squared minus 6x plus 9 plus.
How do I do this?
Yeah.
And then I add 9.
Are you supposed to subtract?
Oh goodness. Yeah, this is kind of, it's like dyslexia, except it's kind of math inversion. I'm adding 18 to both sides. Oh, my notes are correct. Okay, now it's going to work out right. So we've got y plus 5 equals 2x minus 3 squared. All right. So now the vertex is at 3, negative 5. 1, 2, 3. 1, 2, 3, 4, 5. Down here, again, it's times 2, so it's kind of, I'm not going to draw this very well, but it's kind of a narrow parabola. And if we solve this using the quadratic formula, 44 plus minus the square root of negative, sorry, 12 plus minus 144 minus 4ac, that's 8 times 13, 104 over 4. We get 3 plus or minus 40. Square root of 40 over 4. Square root of 10 over 2. Right? That's right. And this tells me where these two zeros are. So what are they? They're 3 plus the square root of 10 over 2. Square root of 10 around 3. So 6, it's around 3. That's over here. And this is closer to 0, but it's not quite. Somewhere over here. And notes I have 1.4 and 4.6, so close enough. So again, the idea here is not you should give up on your technology. You just want to look at a graph. Use a graphing calculator. But you know, if you're on a desert island or you want to understand how this fits together, this is how you can graph a quadratic. Here's a question. What is the minimum here? How can we find the minimum? Well, we know that the vertex is at what? We said 3, well, 3, negative 5. We know what the minimum is. It's negative 5. That's easy enough. You get that for free. All right. We're going to look at that same question, though, in the abstract here. What is the minimum or maximum of this function? And we just did it in an example, but we could do it algebraically and we could learn something. So let's try what I just did, but without benefit of actual numbers. So we have y equals ax squared plus bx plus c. So what did I do? First thing I did is I said a times x squared plus b over 2x, and I left this out here. I guess I could subtract it. And then I wanted to complete the square. So what do I need to complete the square? Where's that? This is over A. 2. Do I need to complete the square here? This is my B is B over A. What do I do with B over A? What do I do with B? Divided by 2 and square. Now, if you're sitting there going, I knew that, but you're sitting there going, remember that. This is really important. Completing the square is a really important skill. Before we're going over it again. We want to add b squared over 2a squared, or 4a squared. So we have to add that to both sides. All right, this becomes a times x plus b over 2a. This becomes y minus c minus b squared over 4a squared. This might look more familiar if I write it this way. 4a squared c. Oh, well, I've got an A over here. I don't have to worry about that. Did I make the same mistake I did here over there? Yes, I did. I added b squared over 4a squared here, but that's times a, so this is just a. Okay, so now if I write this as this is 4ac minus b squared. This should look like the determinant, the negative determinant over 4a, and this is ax plus b over 2 squared. All right, so that tells me where the vertex is, right? The x is negative b over 2a. Just read that off from here. And this is now my no, that's right. This is where it occurs. Its value is now the negative of this, just b squared minus 4ac over 4a. Okay, so now we know where the minimum is, and now we know what its value is. happen to remember this, you happen to write it down in your notes, it's a real convenient way to answer the question, what's the minimum or the maximum here? How would I know whether this is a minimum or a maximum? How can I tell right away? Just by looking at this equation. You look at the leading coefficient. If it's positive, it's going up, so it's a minimum, right? If it's negative, it's going down, it's a maximum. All right, so let's do a real example here using this strategy, and let's do another example, I guess. So we're going to take the function f of x equals 5x squared minus 30x plus 49. So again, we're going to change this to y. And I guess again, I'm just going to skip a step. I'm going to subtract 49 from both sides. And I'm going to factor this out. And I want to know what to add to this. What do I have to add to that to complete the square? I think we've seen this before. Okay, you're all looking at this and going, divide by 2 and square. Thank you. So it's 9 again. This time doing it the right way. 5 times 9, I'm adding to that side. So I have to add 45. So y minus 49 plus 45 is minus 4. This is 5 times x plus, no, not plus, which would be minus, minus 3 squared. So I know that this has a vertex at 3, 4. And I know from the 5 it's pretty narrow. So it's, let's get this right. 1, 2, 3. 1, 2, 3, 4. And its minimum, read right off, is 4. You can also, plus 49. You could also check the determinant here. B squared is 900 minus 4ac. So 20 times 49. It's like 20 times 50. Right? It's 1,000. No, that's 100. No. I can't do this stuff anymore. Times 20 is 80. Well, determinant is minus 20. about the roots. E squared minus 4ac equal to 0. You have one duplicate root. It's greater than 0, you have, well, one real root. It's greater than 0, you have two real roots. And if it's less than 0, what happens? Yep. Oh, okay. Hands waving. What happens if the determinant of a quadratic e squared minus 4ac is less than 0? What do we know about the roots? Okay, let's do a simple example. Negative 1 plus or minus the square root 4ac minus 4ac over 2 plus or minus square root minus 3 over 2. What kind of roots are those? When you have a negative square root, they're complex. So if the determinant is less than 0, you have two complex roots, and call their relationship for the two roots. They're complex conjugates. Okay. They're going to be a plus pi and a minus pi. Here we have minus 1/2 plus square root of, we'll just call it square root of 3i over 2, and negative 1/2 minus square root of 3i over 2 complex conjugates. Okay, so that's functions, one-to-one functions, inverse functions, quadratic functions. I guess while we're at it, we might as well look at this question. What if I wanted the inverse function here? So recall the steps I talked about to find an inverse function. They kind of look already like what we did. We're going to change f of x to y. Well, I went through this little dance here where I found where I completed the square. Let's add 4 to both sides here. Switch the x and y. And then solve for y. So I've already done the hard work here by completing the square. So this becomes x minus 4 plus 5, y minus 3 squared. We find the square root of both sides. I'm going to write this clearly. Move it over here. Again, now, this is not a one-to-one function typically, so we're going to have to make it a one-to-one function. So we're just going to look at the positive square root. We divide. And And now we can just add 3 to both sides. So we're going to get y equals 3 square root of x minus 4 over 5. So that's now the inverse function. So you can find the inverse function of a quadratic this way. All right. Let's take a look. That's enough for today. Any questions? Okay. I'll be around here for a little bit if you have some personal questions.